Study of strength parameter for different drain material using PVD for consolidation of soft clay by radial flow. The rapid development and associated urbanization have compelled engineers to construct earth structures, including major highways, over soft clay deposits of low bearing capacity coupled with excessive settlement characteristics. Consolidation due to radial drainage using PVD is one of the ground improvement techniques in which the consolidation is accelerated by reducing drainage path. Soil improvement is required to provide adequate bearing capacity and improve shear strength of the soft cohesive soils to satisfy the need for various type of construction on sites underlain by such soft soils. Amongst various ground improvement techniques, the technique of preloading or precompression used in combination with vertical drains is one of the oldest and most widely used techniques to preconsolidate and strengthen weak compressible soils. Present research work focuses experimental model of various drain materials like sawdust wrapped with filter paper, SD, sawdust wrapped with geotextile, SDW, sand drain, and jute wrapped with polyamide polyester geosynthetics, JPPG, to expedite the in-situ settlement due to excess pore water pressure dissipation under preloading by radial drainage, taking advantage of having more horizontal permeability than vertical. The hydraulically pressurized row-type odometer was developed in the Applied Mechanics Department of MS University of Baroda, India. The present research work focuses on finding the most optimum drain in terms of materials, both natural and synthetic type, size, diameter of drain, and geometry to accelerate the consolidation of soft clays with a complete setup of hydraulically pressurized modified odometer with conventional Bishop pore pressure measuring system and measuring settlement using a dial gauge. The effect of PVD of N value, ratio of zone of influence to the diameter of drain, of 10, 12.09, and 14.76 on the consolidation characteristics of kaolinitic clay was investigated to study the dissipation characteristics using isochrones and settlement characteristics. Time pore pressure dissipation and time settlement observations were recorded for different applied stresses under long-duration testing. Average degree of consolidation was computed using isochrones. The shear strength of the kaolinitic clay was found out before and after the consolidation test by vane shear test. The shear strength of different drain material is compared, and also consolidation and compressibility of circular and cross-shaped drain is compared for good shear strength. Present work shows the comparison of experimental results of shear strength for all the drain materials. Keywords: vane shear test, shear strength, cross and circular shape, effective shear strength, and value. 1. Introduction. Beginning with the classical work of Terzaghi on three-dimensional consolidation process and thereafter Baron's theory on consolidation due to radial flow, which was further extended by Hansbo. Number of research workers carried out research and focused the attention on various influencing factors of vertical geodrain on consolidation characteristics of clayey soil due to radial flow either by laboratory model or in the field. Most of the soil deposits have greater permeability in horizontal direction, which can be utilized efficiently by the use of prefabricated vertical drains. After the use of sand drains, several new types of geodrain has come on the horizon, with different shapes and material, namely sandwick drain, jute drain, polypropylene drain, cardboard drain, rope drain, etc. At first, three-dimensional consolidations problem was given by Terzaghi, 1923. Prior to this, three-dimensional consolidation problems were solved using one-dimensional approximation to three-dimensional problems using Terzaghi's famous consolidation theories. Further modified in Terzaghi, 1943, and Baron, 1948, reported simplified expression for the design of vertical drains. The theory after Tan, 1961, includes stress-strain relationship for clays during radial flow as a function of time, which he approximately solved using linear, integrated equation. The fourth theory was propagated and enhanced by workers namely Hansbo, 1960, Henrik and Desoyer, 1961, Escario et al., 1961, Tan et al., 1971, and Hansbo, 1981. They have extended the scope of the theory, considering with respect to variable nature of loads, permeability, compressibility, and structural viscosity. The equations of Baron were also used by Rowe, 1969, in analyzing the consolidation of lacustrine, laminated clays. This work was subsequently developed by Horn, 1964, which includes and gives for laminated or layered clays having sequence of identical layers. Beginning with the classical work of Terzaghi on three-dimensional consolidation process and thereafter Baron's theory on consolidation due to radial flow, which was further extended by Hansbo, number of research workers carried out research and focused the attention on various influencing factors of vertical geodrain on consolidation characteristics of clayey soil due to radial flow either by laboratory model or in the field. Most of the soil deposits have greater permeability in horizontal direction, which can be utilized efficiently by the use of prefabricated vertical drains. After the use of sand drains, several new types of geodrain has come on the horizon, with different shapes and material namely sandwick drain, jute drain, polypropylene drain, cardboard drain, rope drain, etc. At first, three-dimensional consolidations problem was given by Terzaghi, 1923. Prior to this, three-dimensional consolidation problems were solved using one-dimensional approximation to three-dimensional problems using Terzaghi's famous consolidation theories. Further modified in Terzaghi, 1943, and Baron, 1948, reported simplified expression for the design of vertical drains. The theory after Tan, 1961, includes stress-strain relationship for clays during radial flow as a function of time, which he approximately solved using linear, integrated equation. The fourth theory was propagated and enhanced by workers namely Hansbo, 1960, Henrik and Desoyer, 1961, Escario et al., 1961, Tan et al., 1971, and Hansbo, 1981. They have extended the scope of the theory, considering with respect to variable nature of loads, permeability, compressibility, and structural viscosity. The equations of Baron were also used by Rowe, 1969, in analyzing the consolidation of lacustrine, laminated clays. This work was subsequently developed by Horn, 1964, which includes and gives for laminated or layered clays having sequence of identical layers. 2. Vane shear test. The Vance shear test is used to measure the shear strength of cohesive soils and for the soils of shear strength less than 0.3 kg/cm2 for which unconfined tests cannot be performed. This test gives the undrained strength of the cohesive soil. This test can be done in laboratory or in the field directly on the ground. Fig. 1 Vane shear apparatus with soil sample. 3. Scope and objective. The hydraulically pressurized odometer, row type, with central geode rain is employed in present investigation and CVR value is determined for both settlement and pore pressure readings. Measurements of pore pressures are planned to carry out by conventional Bishop's pore pressure setup and extensometer. It is intended to conduct a series of consolidation tests with radial drainage through vertical geode rain centrally placed and measurement of settlement and pore water pressure at 3 radial distances will be taken so as to prove efficacy against various physical factors namely type of drain material, shape, aspect ratio, various shapes of drain, and value, i.e. different diameters of drain related to influence zone. In present investigation it is intended to use sand, sawdust wick, jute, polyamide polyester geosynthetics to fabricate the vertical geode rains of different diameters in relation to diameter of hydraulically pressurized odometer, row type, is used which has special facility for measuring pore pressure and settlement during consolidation due to radial flow of water. The present investigation will simulate the theoretical values of degree of consolidation with experimental values for all n values where n equals radius of odometer to radius of the drain. 3. Laboratory investigations. 3.1 Materials used. The soil used for this investigation was clay mineral kaolinite obtained communally in the form of powder. To ensure full saturation of the sample the clay was mixed to form slurry with twice the liquid limit using IJERT distilled water. Properties of PVD drain material. In present investigation, sawdust wrapped with Wattmann filter paper, SD, sawdust wrapped with geosynthetics, SDW, sand drain, and jute wrapped with polyamide polyester, JPPG, is used for investigation. The properties of the drain material are shown in Table Point 2, Table Point 3, Table Point 4 and Table Point 5. The sawdust is treated chemically and then used as a drain by encasing it with Wattmann filter paper. Method of soil preparation. The soil used for this investigation was clay mineral kaolinite obtained commercially in the form of powder. To ensure full maturation of the sample the clay was mixed to form slurry with twice the liquid limit using IJERT distilled water. Density was sufficiently low to allow the removal of entrapped air when the sample in the consolidation cell was vibrated. The slurry was transferred into the odometer after the cell body had been lightly coated with a thin layer of silicon grease to minimize side friction. The odometer was then placed on a handle-operated vibrator and vibrated for approximately 1 hour after which only occasional air bubbles could be seen on the surface. The clay was then scribed level. And a filter paper followed by a porous stone was placed at the top. The sample was then pre-consolidated under gradually applied static dead load of 8 kPa, with .P/P equals 1 kPa, 2 kPa, 4 kPa, 8 kPa, so that the consolidation occurring is normal. These increments are given by means of dead load with porous stone on the top of the clay sample topped by filter paper so that sample during consolidation water gets removed through porous stone. These increments of static loads are to be kept for a longer period of time, at least 48 hours. Increments are calculated as shown below. Representative sample for determination of water content was taken and measured. Initial strength was measured by vane shear in separate crucible of vane shear apparatus by dead loading in same fashion by small weights. To avoid the soil structure disturbance of soil cake prepared. Initial height was measured with pointer arrangement with stand and the extra soil was trimmed. Filter paper is kept on the surface of the trimmed soil and rigid perspex plate was laid on it to create the equal strain condition while loading. Installation of drain. The axial hole was formed with a thin-walled mandrel, having area ratio of 0.8 to 1.6 attached with template and guide frame. Circular filter paper of size PVD is lowered in the bore hole. A drain hole was then flooded with water from the central connection to the reservoir. The drain was filled with IJERT saturated PVD drain material with the aid of small diameter flexible tubing by siphoning action without any smear and without any intrusion of clay and PVD to avoid blockage. The top cover is then seated into position. Installation of vertical drain. 3.6 Test procedure. After the cell is sealed, settlement dial gauge and Bishop pore pressure measuring apparatus were connected at their respective location. The first pressure increment is applied through the flexible convoluted jacket after closing the drainage control valve and settlement gauge reading is recorded. After completion of consolidation process drainage control valve was closed then the next increment of load is applied and the same process is repeated for a series of various pressure increments, with P/P equals 1.0. The loading was done in the increment of 20, 40, 80, 100, and 60 and 320 kPa keeping P/P equals 1. After the completion of the test, vane shear test was performed at 3 locations to determine the gain in strength due to dissipation of water. The value of settlement and pore water pressure is measured with respect to time, and coefficient of radial consolidation is calculated. Shear strength variation radially. Initial shear strength was measured using vane shear apparatus. A soil sample in separate crucible of vane shear was prepared and was pre-consolidated by dead loading in same fashion by small weights. This was done to avoid the soil structure disturbance of soil cake prepared. The final shear strength was also measured for all 4 drain materials. The final strength variation was calculated using vane shear test apparatus after each experiment at radial distance for all drain material. The shear strength was measured at the top surface of the cake at a distance R1, R2, R3 from the central drain. 4 tests and result analysis. 1. The shear strength for SD, SDW, sand drain, and JPPG drain are 98 kPa, 114 kPa, 100.6 kPa and 126 kPa respectively. 2. It is observed that the gain in strength of the consolidated mass is better in JPPG drain in comparison to SDW, sand, and SD. 3. The effective shear strength was calculated for all drain materials. Comparing the effect of various drain materials, the effective shear strength, SE, achieved at end of consolidation is observed that JPPG, 101 kPa, and SDW, 103 kPa, exhibit more strength as compared to sand and SD. 4. The sand drain and sawdust exhibit almost same effective strength of 82 kPa while SDW and JPPG exhibit same order of 102 kPa. 5. Conclusion. It is observed that mid-plane strength in every material is higher compared to near the drain and at farthest radial point. Average percentage increase of shear strength from near the drain to mid-plane is 46% while decrease of strength from mid-plane to farthest point is 66%.